Hello everyone. My name is Kunal and I'm your physics tutor and we are actually doing oscillations and today is our lecture number 9th. Let me quickly recap the things कि हमने previous class में क्या-क्या चीजें cover करी थी. So in previous class we actually deal with the things like angular, simple, harmonic motion. हमने जिसमें बहुत सारी equations पे बात करी थी like angular displacement as function of time, right? And angular velocity with function of time, angular acceleration as function of time, torque as function of time and all, right? And after that, we deal with the system, which is actually known as simple pendulum, जिसकी हमने time period calculate करी थी, which is actually is equal to 2 pi root under L by G, right? So in today's class, we're actually deal with the simple pendulum, but it is actually attached in different kind of frame as we already seen in our previous class. The first example in which our simple pendulum is actually attached with the ceiling of the lift, in which we get the time period is actually equal to 2 pi root under L by A naught plus G, in which the lift is actually moving with the acceleration A naught in the upward direction, right? And here is our simple pendulum attached. So these are the things that we are covered in our previous lecture. So let's begin with a system in which our simple pendulum is actually attached to a accelerating car. So take it as question actually, in which our simple pendulum is simple pendulum in actually accelerating car, right? So this is actually the road, and this is actually a car in which from its ceiling a simple pendulum is actually attached, and the car is actually moving with the acceleration A naught in its rightward direction. So you have to find the time period of simple pendulum in this frame. So what we have to do, we have to go through the force method. So let's first write the equation at the mean position, and then we have to write the equation at the displaced position, and then we have to find the relation using the mean position equation between acceleration and the displacement from its mean position, or angular acceleration and the displacement, or the angular displacement. And so we can get the omega, and so we can find the time period with the help of 2 pi by omega. So let's start solving. So let me make the frame here. This is actually inside the car where pendulum is attached, right? And let us suppose that at some angle theta is equal to theta naught, right? Because everywhere like two forces acting. One force is like mg is acting downward, and pseudo force is actually acting in the backward direction because our car is actually moving in the forward direction, right? So actually pseudo force is acting on the backward direction, and we are assuming that at some theta is equal to theta naught, we have actually net force is equal to 0, so we can call it as a mean position, right? Because at theta is equal to 0, we don't have mean position because we don't have torque is equal to 0. Because at theta is equal to 0, again, the force is actually acting in the backward direction, which is ma naught. And we have a torque, which is, if its length is L, so m a naught into L, there is a torque exists at theta is equal to 0. So I am assuming that at some theta is equal to theta naught, we have a net torque on this system is actually 0. And this whole system has an amplitude, you can say, or the angular amplitude as theta. So we are assuming that. So we have to go through the dynamics of the particle. So let's take the dynamics of particle. So from the dynamics of particle, what we can conclude here is net torque about suspension point. This is actually we can call it as suspension point. So net torque about the suspension point is actually zero because we are writing the equations at the mean position. And at mean position, we have actually needed the net torque is equal to zero. So we have to write the all of the torque due to this. So we have to take the component, right? So if I take the component of mg, so it will be in this direction, and it is actually mg sine theta naught. And when I'm considering the component of this force, pseudo force, so it will be in this direction, which have actually due to torque, and this is actually equal to m a naught cos theta naught. And due to the both of the component mg sine theta naught and m naught cos theta naught, we have a torque and both were in actually opposite direction. So we can write here mg sine theta naught into L is equal to m a naught cos theta naught into L because torque is equal to R cross F, right? From this get cancelled, and what we get tan theta naught is equal to A naught by Z. So we are concluding here at theta is equal to theta naught, which is actually tan inverse of A naught by Z. So at this angular displacement, we have actually mean position, right? That means at theta naught is equal to tan inverse of A naught by G. At this angular displacement, we have actually mean positions. All right. I hope it will be clear to all of you what I'm trying to say. So now we have to write the equations at displaced position, right? So we have to write the same dynamics because we get the uh, mean positions, which is actually at the angular displacement of tan inverse of A naught by Z. Now we have to write the dynamics of the particle at the displaced position. So what I'm trying to assume is our particle is actually displaced from its mean position by angle of theta, right? We are actually assuming here. Let me write it here. We are assuming particle has a particle has a amplitude or angular displacement from its mean positions is theta, right? This is actually I'm assuming. So we have to write the dynamics at displaced position, or we can say extreme position as well. So let's start writing the dynamics of the particle. So we have to write the restoring torque about suspension point, right? This is actually our suspension point, and we have to look at here. The everything will be same. The only thing changes is right theta naught plus theta because these are the only two forces due to which our net torque is happening, right? So these are the two components like ma naught cos theta and mg sin theta naught. So we have to just add the angle of theta because theta is our net angular displacement from its mean position. So we can write it here mgl sin theta plus theta naught minus ma naught, and both were in opposite direction. So if I am assuming clockwise is positive, negative, so anti-clockwise is positive. Ma naught L cos theta plus theta. You can write it here. We are actually assuming clockwise as negative and anti-clockwise as positive. You can look at from here as well, right? The direction of torque by ma naught cos theta plus theta naught is actually in this direction, which is actually clockwise. So we are considering it as negative and anti-clockwise as positive. Now we have an actually relations from the mean position. What we have to do in we are actually try to find the time period using the force method. Earlier we had discussed about this. We have actually two methods to calculate the time period of the any system, any oscillating system. The first method is force method, and the second method is energy method. And here we are actually using the force method. So we have to write the equation at mean position. We have to write the equation at displaced position. and we have to use the equation of mean position and displaced position to write the relations between angular accelerations and the angular displacement. So we can calculate the omega square term here. So we can get the time period. So now we are gonna using the relations, which is actually tan theta is equal to a naught by z, right? We have an relation. Let me write it here. We have an relation. We have an relation tan theta naught is equal to a naught by b, right? And I hope you all know that this is actually p by b. Perpendicular by base is actually tan theta. So similarly, we can writing from mean position, right? So we have actually derived one more equation, which is actually is equal to sine theta naught is equal to actually actually sine theta is e by h, right? So this is actually a naught square plus g square. Similarly, we are actually cos theta naught is actually equal to g by a naught square plus g square, right? Now we have to use one approximation. Why? Because we are actually dealing with the simple angular simple harmonic motions, right? We are not actually dealing with the oscillation motion. We are actually dealing with the simple harmonic motion in which the net torque is a linear function of the angular displacement. So we have to use, as we using the approximation in previous class, so we have to use an approximation here, which is actually theta is tending to 0. So look at here, when our theta is tending to 0, so our sine theta is equal to theta and cos theta is equal to 1, right? So here we can write our restoring torque as, look at here. If you break this term using the formula, let me write it. If you all know this, like sine of A plus B, exactly sine A cos B plus cos A sine B, right? And cos of A plus B is exactly cos A cos B minus sine A sine B, right? So we are actually using these two formula, and then we are gonna substitute this term A naught by sine theta is equal to, and then we are gonna calculate the restoring torque here, right? So let's start doing here. So just open this term sine, take it as sine A plus B, right? Take this term as written as sine of A plus B, and take this term as like sine cos of A plus B, and start writing here. And using one approximation, where sine theta is equal to theta and cos theta is equal to 1. So when you do so, let's start doing it. Will be like ml. Take ml as a common, so it will be like g sine theta cos theta naught plus g cos theta sine theta naught minus a naught cos theta naught and plus a naught sine theta, right? I'm just opening these two of terms, taking ml as a common and just opening the sine theta plus theta naught as sine of a plus b. There will get ml, and this term is become 0 because when theta tending to 0, sine theta is equal to actually theta, right? So we can write it from here is, and cos theta naught is, the value of cos theta naught is g by root under a naught square plus g square. So it is actually equal to g square theta by root under a naught square plus g square. Plus here we can write from this equation is a naught by g plus a naught square plus g square minus a naught g by root under a naught square plus g square and plus a naught square plus a square theta by root under a naught square plus g square. So this and this term get cancelled. So what we will get from here? We will get our restoring torque is equal to ml root under a naught square plus g square into theta. So here we can write it as, and we have actually, this is actually important problem, right? So you have to look into this problem as in very careful manner. So let's take here, what we can do here is, okay. So let's start writing. So it will be like ml square into alpha is equal to ml root under a naught square plus g square into theta. This get cancelled. So we get the relation like root under a naught square plus g square. I hope there will be like dent of this. So it will be like omega square is equal to a naught square plus g square by L. There is some calculation error. Okay. Before I'm writing omega, I just put the right. So omega square is actually equal to a naught square plus g square by L. So we have actually time period is equal to 2 pi root under 2 pi by omega. So it will be like L by a naught square plus g square by L. This is actually our omega square. So this is actually our time period when we have a simple pendulum is attached to the ceiling of the accelerated car. So we have actually, if the acceleration is a naught, so our time period is 2 pi root under L by a naught square plus g square, right? So now if you look at this problem, we have to use the multiple kinds of approximations at each stage, right? We have used the one approximation there and we have used one more approximation earlier, right? So, but we have to solve this kind of problem in a very few seconds, right? Because these are uh, somewhere these are treated as tough problem. But as for your JE aspirant, so it is you have to deal with this kind of problem in a very easy manner. So let's talk it about some kind of short trick using the just the vector additions kind of thing. So you can analyze. So first thing you can analyze here is if this is actually our first I'm gonna tell you the trick, then I'm gonna apply the same trick on the above accelerating car system. So you can connect it with in a well manner. So let's start. Right. So we have to find the time period of simple pendulum under influence of other forces, right? So we have to, it is actually 2 pi root under L by G effective, right? Effective acceleration we have to write. Like in normal pendulum, what actually in normal pendulum where the only force is acting is force of gravity. So in this case, the time period is actually equal to 2 pi root under L by G. But when our simple pendulum is under the influence of some other kinds of forces, like when it's kept in lift, in accelerating car, in uh, in some kind of things which are actually have acceleration. So it is under the influence of some other kind of forces. So our time period changes. So in that cases, we have our time period is actually 2 pi root under L by G effective. And where what is actually G effective? So it is actually simple, the vector addition kind of thing. So it will be like G square plus A naught square plus 2 A naught G cos theta, where actually A naught is accelerations due to other forces and theta is actually the angle between A naught and right. So these are the two things that you have to keep in mind, and this is actually the shortcut. You can write directly if your simple pendulum is kept anywhere where it is under the influence of some other kind of forces. So let's try to verify in our previous system, right? On this system, when our simple pendulum is in accelerating car. So let me write it here, the verifications, right? So let's verify here. So this is actually important and important short trick. So let me put it under a box to highlight this thing. Okay. So verification with our previous system. So we have a car, right? And it is actually accelerating with an acceleration A naught. And there is actually our pendulum, which are actually under two kinds of, which are actually under the influence of two kinds of forces. One is actually gravity force, which is actually acting vertically downward, and one is actually pseudo force, which is acting in the backward direction, which is actually ma naught. Right. So these are the two kinds of forces which are influence our simple pendulum. So what we have to do, we have to, our time period is, we actually know the time period is actually 2 pi root under L by G effective. And we have to find the G effective here. So G effective formula is G square plus A naught square plus 2 A naught G cos theta. Right. So here actually our A naught is the acceleration, the only acceleration due to the other forces. And so we can write G square plus A naught square plus 2 A naught G. Now, what is the angle between the A naught and the G? So the angle between A naught and the G is actually 90 degree, because one force is acting vertically downward and other force is actually acting vertical back in backward direction. So the angle between the acceleration due to the pseudo force and the uh, acceleration due to the force of gravity is actually 90 degree. So we have to write it here, the cos 90 degree. And we all know that the cos 90 degree value is 0. So this whole term is treated as 0. So our G effective value is root under A naught square plus G square. So we can directly say our time period is 2 pi root under L by A naught square plus G square. So this is the actually we can calculate in just 2 or 3 lines, in which if we are gonna solve by via method, so it will take lots of approximation and lots of calculation as well. So via short trick, you just calculated the time period in just actually two steps. You just have to calculate the G effective, and on calculating the G effective, you have to just think about the two things. The first thing is actually what are the acceleration due to the other forces, and the second thing you have to think is what is the angle between the uh, acceleration due to other forces and the force of gravity, right? So these are the two things that you have to only think about, and other thing will be in doing in a simple. So these are the things which actually based on simple pendulum. So let's do some kind of problem in it, and then we are moving to our next topic, which is actually compound pendulum. So let's take some questions here. So there is our actually a simple pendulum, okay, which has a length of a string is L, and it is actually dipped in water, right? It is actually dipped in water, and there were several things is given. The first thing is given is sigma, which is actually the density of the particle, and rho, which is actually the density of the liquid. So this thing is given, is the only given, and the length is obviously given. And you have to calculate the time period of the simple pendulum. So we all know that whenever some particle is dipped in some kind of liquid or some kind of water, so there is a force is actually acting by the fluid, which is actually termed as buoyant force, right? Force of buoyancy. and its formula is actually F Binand force is actually V rho G. Right? We all know that whenever some particle is dipped under some kinds of fluid, so the fluid exert a force which is actually in vertically upward direction, which is actually known as Binand force. So we are actually on this simple pendulum, we have actually two kinds of forces. That means we can say that our simple pendulum is under two kinds of under the influence of two kinds of force. First is actually our normal gravity force, and the second one is Binand force. So let's start thinking and try to find the accelerations and acceleration by the other forces, and then we are gonna calculate the G effective. So we all know that our time period is nothing but 2 pi root under L by G effective. Now we have to calculate the G effective. So we all know that first I'm gonna write it here. G effective is G square plus A naught square plus 2 A naught G cos theta. Now look at here. The mg force is actually acting vertically downward, and V rho G, right? V rho G. So there is actually density is given. So we all know that volume into density is actually mass, right? So we have to write the volume. So we have to do like m by sigma, and it is actually dipped in the fluid which has a density rho. So rho and G, right? So we have the accelerations, which is A naught when we divide it by the, this is actually our FB. So FB by M. So when you do so, you will get rho by sigma into G. This is actually our A naught value, and both were in opposite direction. So our theta is actually equal to pi, or we can say 180 degrees. So let's apply and try to find the value of G effective. So here it will be equal to G square plus A naught value is nothing but rho square G square by sigma square plus 2 A naught. A naught we can write it in a later phase, and G, and cos theta value will be cos pi. So let's start writing here G square plus rho square G square by sigma square plus A naught will be like 2 rho G square by sigma, and here it will be counted as minus. So when you look this whole term, it is actually written as in the form of G minus rho G by sigma whole square, right? Because A minus B की whole square के term में लिखी हुई है ना सारी term. So you can write this as G1 minus rho by sigma. So this is actually our G effective. So our time period is nothing but 2 pi root under L by G effective. So here it will be like 2 pi root under L by G1 minus rho by sigma. So this is actually our time period of this simple pendulum, which is actually dipped in the fluid. So let me give it the heading here. Simple pendulum. Right. I hope it will be clear to all of you what I'm trying to say, right? It just is you have to write the other forces which actually has influence on our simple pendulum, and you have to just write the G effective, and then you are easy to write the time period, which is actually 2 pi root under L by G effective. Now let's take our last system, and which is actually based on this is actually our wedge, in which our actually there is a box under which there is a simple pendulum, right? And this is its mean position, obviously. Somewhere it has mean position. So, and coefficient of friction is 0. That means the surface is smooth, and the wedge is inclined at the angle of theta. So you have to find the time period of simple pendulum. Okay. So you have to first write the dynamics of the pendulum here. So we can write it here like mg force is actually acting vertically downward, right? And there is a force, which is actually mg sine theta, which actually pseudo force is actually acting in the backward direction with the a naught is equal to g sine theta, right? And so this is actually our system. We have acceleration g in this direction, and we have a at angle of some theta, theta dash, we can say. We have because we have already the wedge is actually inclined at angle theta. So so I'm using some other angle between to represent the angle between acceleration of other forces and acceleration of gravity. So in this direction, our like a naught, right? And it is actually equal to nothing but it is actually g sine theta. This is actually our pseudo force, pseudo acceleration, you can say. And how to find this angle? So this is actually our angle, right? This this is actually our angle. So if you consider this angle, so this is actually our 90-degree, and this angle is theta. So this angle is also theta. So our theta dash is equal to 90 plus theta, right? So now your time to find the G effective. So our G effective value is G square plus A naught square plus 2 A naught G cos. The angle is actually 90 plus theta, which is actually is equal to minus of sine theta, right? Let's see what is actually going on. So it will be G square, A naught square will be like G square sine square theta. And here we will get 2 A naught because cos 90 plus theta is actually minus of sine theta. But somewhere is else, there is something else, right? Let me write it here, which is actually 2 A naught G sine theta. Uh, Actually, G square sine theta. G into G we can write because our, and there will be like minus sine theta. So here we can write minus of sine theta. So what we get from here, let me do a fresh calculation here. Otherwise it seems like, okay, so let's do a fresh calculation here. So it will be like G square plus G square sine square theta plus 2G square, and cos 90 plus theta is obviously minus sine square theta because sine theta and it will be like same. So here we'll get G square minus G square sine square theta. So when you take the G square common, so you'll get 1 minus sine square theta. And this is actually equal to cos square theta. So we'll get G cos theta. So here our G effective is nothing but G of cos theta. So our time period, our time period is actually nothing but 2 pi root under L by G of effective. So it is actually equal to 2 pi root under L by G of cos theta. So this is actually our time period. When it is actually our simple pendulum is actually hanging on the ceiling of the inclined wedge. So that's all for today's. In tomorrow's class, we are going to discuss our new system, which is actually termed as compound pendulum. And then after we are going to look some problem based on what we can say, small oscillations, force oscillations, and damped oscillations and all. So, okay, that's all for today. Thank you.